All right, hello, and good afternoon, and welcome to Chapter 3. So today we are going to go over Chapter 3, and let's get right into it. Today we're going to talk about network protocols and communications, the standards. We'll talk about the OSI model and how does it relate to the TCP/IP model, and how the encapsulation process, how data gets encapsulated when from the network layer all the way to the physical layer. So I'll get into details. It's pretty much the same as if you are trying to send a package over, send it over to the postal to the United States Postal Service, and there is a standard on how you should encapsulate your packet before you send it out. We'll discuss all of that as we move along. All right. So here are the objectives for this chapter. So you'll learn about the rules on how to facilitate um, the communications between you and the destination. Okay, hold on a second. All right, continue. So here are some rules of communication. In this chapter, we'll cover those four sections: the rules of communications, the network protocol standards, the data, the moving the data in the network, really the encapsulation process. Excuse me. So let's get busy. What are the rules of communications? So when you want to communicate with someone, for example, the rule is if you are speaking, the other one has to listen, and if he or she's speaking on the other end, then you have to listen. So that's a standard. In data communication, there are pretty much the same thing. You take a message, you send it to an antenna, which is the transmitter, and that transmitter will send it either in the air or on a wire. That's your transmission media. And on the other side, the signal will be received and decoded by the receiver, interpreted, processed, and they communicate back and forth. Pretty much, they can use the same medium. So same idea with data communications. All right, there are some rules that you have to use. uh, for example, the common language and grammar. With data communication, you have to have the same protocol. How do you encapsulate the data? Where do you place all the labels so that the other person on the other end that is speaking the same language knows where to read these labels that are on the packets? For example, if you send um, a package in the mail and you put the source address anywhere you want or the zip code anywhere you want, you write the numbers all over the place, that's not going to work, right? Post office will not send your package, and if you're lucky, you'll get it back. All right. Also, you may go to the post office and say, "I want a confirmation and an acknowledgement that the receiver has received the package." So he'll probably charge you extra money for that certified mail. Same thing with data communications. If you need a confirmation and an acknowledgement when you send out your data, that means you are going to use the TCP protocol, and the TCP protocol will charge you time and a little bit of delay in getting your data to the destination because it's going to make sure that the other guy received it. But if you want to go the least expensive way, then you use UDP, the user data program. It just sends it as quickly as possible with zero delay almost. All right, so there are some rules, as we will discuss later on, that are very similar to sending your package through the postal service. And we'll use that analogy as we move along. All right, so when you communicate to conserve bandwidth, bandwidth is the amount of data that you are going to send on a transmission medium. So let's say you have a pipe that is only the diameter of that pipe has a certain length. And if you want to send as much data as you want, it's a pretty good idea if you can just send codes in here, which is a small amount of data that can be going through this pipe, the bandwidth. So this way, if I send a small amount of data, more data can be sent, more codes. And on the other end, all you got to do is decode the data, figure out what the code is, and get the message out. Now, remember, you code using an encoder. Take your message, you encode it, and then you send it out. Put out some codes. and the other guy on the other end receives the codes, decodes the data, and gets the message back. Now, the coding and encoding, the encoding and decoding of the data has nothing to do with really encryption. The codes, everybody knows it. It's just the idea is to conserve bandwidth, really, what it comes down to. Okay, so Ethernet, token ring, fiber data distributions, the different types of Ethernet, 10 base 2, 100 base 2, even a gigabit Ethernet, use different types of coding so they can get their data and conserve bandwidth as much as they can. All right, so the idea of message formatting. So let's say you want to send a box, a big box in the mail. So you take it to the mail office and you have to write the username and password, username. I mean the user, who you're sending the data to. This is you. Your source IP address, your source address, the street number, the city and state, and whoever, the destination. There's name, city, state, street number, everything. And it has to be on the top left-hand corner, the source address, and the destination has to be in the middle if you're sending an envelope. You can't write the destination address any way you want, so that's the rule. The zip code has to be at the end. So post offices, when they receive this envelope, are just like routers. They look at the zip code. Routers look at the IP address to determine where this envelope, where this letter is going to. So pretty much the same thing, and you need to encapsulate it in a certain length. The envelope has to be of a certain length. The amount of data that's in there has to be a certain amount of data. You can't just put anything you want in there. It cannot, cannot be very, very big, and so on. So all of that is pretty much the same thing that you would do with a piece of data. So going back, let's say you brought in a big 100-pound box to the post office, and then the post office tells you, hey, wait a second, we do not transmit 100-pound boxes. Our maximum is 20 pounds. So what are you going to do? You're going to go back home and put all the stuff that you put in that 100-pound box into smaller little boxes, 5 little boxes, and then you relabel them. Put the source and destination addresses on each of the boxes, because that's the limitation of your post office. Same thing with your data. The first thing that your computer will do, looks at the message that you're trying to send and will chop it up into little pieces, because it knows that your Ethernet NIC cannot have more than 1,500 bytes in it to transfer data. The packet that you are going to encapsulate in a frame, the frame is the type of data that's going to be transported on the wire. That packet that goes inside that frame cannot be larger than 1,500 bytes. Okay, so therefore data has to be divided into smaller pieces all the way from the top before it gets encapsulated. So the message size is limited to a certain amount. And then how do you send the data? Your NIC has to take the data and put it on the wire. So there has to be an access method. This is like you're trying to get on the highway. What is the rule for accessing the highway, the segment? You have to stop, take a look, make sure that there is no traffic before you enter the highway, right? Flow control means that you got to make sure you don't overflow the receiver. He might be too busy, so you don't want to send him too much data. If he's a slow person in processing the data, and let's say you're running at 100 megabits per second, and that other guy is running 10 megabits per second, he has to be able to tell you to slow down a little bit. Don't send me too much data, right? So he can have enough time to process it. And if he's not doing anything, you want him to tell you, hey, could you speed it up a little bit, because I got nothing else to do. Let's get this over with. So that's called flow control. The communication between the sender and the receiver, especially the receiver, is telling the sender to either speed it up or slow down. All right, and response timeout. If there's a certain amount of time, if I don't hear from you, then I have to resend you. I'm going to assume that the data got lost, and then I'll send the package back again. So that always happens with data communications. Another thing you need to remember: once a packet leaves the sender, it never comes back. If it got lost, Nobody sends it back to you. It gets dropped somewhere on the network. And the reason for that, you don't want to create traffic and bringing that packet back to the sender, because the sender can always recreate that packet and retransmit it. There's no resend. It's not like in the post office you want your package back if it doesn't get to the destination, or if the destination doesn't exist. All right, now when it comes to message delivery, there are three different ways or three different options that you can deliver your message. You can deliver it to one person. You want one package to go to one guy in your LAN, so that's called unicast. You can do it to multicast, send it to a certain, more than one person in the same LAN at the same time. We usually don't do a lot of multicasting in our CCNA course. And the third type is broadcasting. That's when you want to send a piece of data to everybody in the LAN. All right, and that's what, as long as you are physically connected to the switch, then you are in the same broadcast domain, which means you will receive every single broadcast message that is coming into this switch. And that's what really logically a LAN is. A LAN is a broadcast domain. All right, so question number one that you should answer: what are the three different message delivery options? And they are unicast, multicast, and broadcast. Let's move on. Don't forget, these questions you have to answer on a separate Microsoft Word document and submit that as homework for Chapter 3. All right, let's continue. Let's go into the network protocols and standards and see what they are. Okay, so as we've discussed earlier, there are some rules that you have to follow when you're communicating. Everybody needs to take turns, for example. You need to know the codes that you are using when you are communicating, how fast data should be sent, all of that. So, that's why everyone should have, for example, the same NIC, because the same NIC has the same certain rules that they need to follow. And if you follow the rules, then communication will be much, much easier. All right? There are some network protocols that you need to follow as well. For example, how is the message formatted or structured, the type of frames, the type of packets that you have, the process by which the networking devices share information about the pathways, for example, the routes, the routing protocols. Routers talk to each other, and each router says to the one next to it, this is the network that I have attached to me. This is like post offices telling the other post offices, hey, if you want to reach New York City, New York City is attached to me, so just let everybody knows out there that they can send the data down to me, because anybody that wants to send data to anyone in New York City, that's my LAN, that's attached to me as the router, send it to me. And routers will pass that information to all the post office, all the routers around the nation, and then they'll find a path to get to the router or the post office to New York City, and that's how routers talk to each other. That's called routing protocols, which we'll discuss that next semester. We'll get to that later on, though. All right, so they also can set up and terminate data transfers between sessions. This is like the old operator that used to set up a communication session between two different people. Now it's really done, or a switch used to do it for the telephone system, electronic switch. Now we have really software that does that over the IP network. Okay, interaction between the different standards. For example, an application protocol such as the hypertext transfer protocol, that is the one that transfers data from a World Wide Web server to your web browser. HTTP has to be able to communicate with the TCP protocol. These are four different layers. An application protocol is the one that what service are you trying to send? And the application protocol has to pass the data to the transfer protocol, where the transfer protocol sets it up for transmission. He's the one who is responsible for identifying what the application is, chopping the data into smaller pieces if the data is, if he receives the data from the application layer and the application layer is too big, he chops it up and he makes a phone call to the destination, and tells the destination, are you there? You know, TCP is a connection-oriented protocol, as we will discuss later on. All of that, once he sets that up, TCP then passes the data to the IP protocol, and he is the one that places the IP addresses, the zip codes, right, on the packet, and puts a whole bunch of other labels on it too. And then the IP protocol gives that packet to your NIC. That's where the network access protocols are, the data link and the physical layer. You know, and that packet then is encapsulated in a frame before it's placed on the physical wires, the media, or it could be the air. So protocols at each layer have to be able to communicate with each other, but they work independently, really, when it comes down to, you know, independent of what this guy is. Once you, for example, once TCP finishes encapsulating and putting all the labels on the segments, he gives it to the IP, and in the IP packet, he doesn't care what the segment is and what's inside it. He just puts it into a packet, labels the packet, and then gives it to the your Ethernet NIC, for example, or your wireless LAN NIC, 802.11 NIC, and then they'll label those frames and send it on its way out. Here are a whole bunch of different standards suites that are being used out there. The old Novell and AppleTalk are pretty much obsolete nowadays. Really, the only one that, even the ISO is hardly ever used. The one that is mainly used is the TCP/IP protocols. Here where you have your application layer protocol, you have the TCP and the UDP protocol. They communicate with each other like we said earlier. Like DHCP sends the data to UDP, HTTP will send the data to TCP for transportation. This is the transport layer right here. And then these guys will do whatever they need to do to the data that came up from upstairs, then they give it to the internet protocol, which is right here, that's the IP protocol. If you're running IPv4, then you label then you place your packet, the segment into packets, in IPv4 packets, put IPv4 addresses and a whole bunch of other labels on it before you give it to your Ethernet or frame relay or your wireless LAN NICs before they send it out. If you're using IPv6, then you use IPv6 labels and packets before you give it to the Ethernet NIC to be sent out. So it's just like an assembly line. And all of this is happening inside your computer before it's given to the NIC on the way out. All right. TCP/IP was designed from the late 1960s to the early 1970s, where the U.S. Department of the DOT, the Department of Defense, wanted to have the Advanced Research Project Agency network. They wanted everyone to be able to communicate with each other regardless of what platform they had. In other words, they wanted somebody, for example, in New York City to communicate with somebody in LA, even if they were running different operating systems, different platforms. So, and that's where TCP/IP came into play. And it just grew right after that. And that's why, you know, all the internet is pretty much was for free for many, many years because, you know, taxpayers funded all of this. All right, here is the TCP/IP protocol, 4-layered protocol. You got the application layer, the transport layer, the internet layer, and the network access layer. Okay? For example, at the application layer is a whole bunch of different application, or sometimes they call them services. For example, if you send emails, you need to send your email to an SMT, Simple Mail Transfer Protocol server. When you receive email, you either receive it from a post office protocol server or an internet messaging access protocol server. These are applications. Let's say you want to send an email. You write your message, and you probably would write whoever, you know, the email address of that somebody that you're trying to send the email to. Once your message is done, then your data is passed to TCP. All the email protocol use TCP to transport their data. So they'll pass that message that you created to the transport layer, TCP. Then TCP takes that message, divides it into smaller pieces. We call those pieces segments. and then he puts a port number on each of those segments to indicate what type of application being used. Okay, so port numbers are placed at the transport layer. And then after that segments are, and each segment will also, oops, let me just go back. And each of those segments also will get sequence numbers to indicate what, who's the first piece, the second piece, the third piece, and so on. And then you pass that data to the IP protocol, so they can be going into a packet. And on the packet, you put the IP addresses. The IP addresses usually identify the location of where you are. Okay? It's like a zip code. And then you give that packet to your NIC. And your NIC will place the packet into frames. And on the frames, you put the physical addresses, the MAC addresses, before they get sent out. All right, so question number 2. What are port numbers used for? Port numbers are used to identify what application is being used, and they are attached at the transport layer. What are IP addresses and where are they attached? IP addresses are used to identify the location or the network, the LAN, it's like a zip code, the LAN where the packet is going to reach, the area. Okay? That's what the IP address identifies. And it's placed at the internet layer. In this case, if it's a TCP/IP protocol. And what are MAC addresses? MAC addresses identify the host inside a LAN. Now, MAC addresses, which is sometimes called the physical address, is placed on the frame, and you can only send frames from one device to another directly connected device. Directly connected means you can see it, you can physically send the data packet. Package has to go from one device to another device to another device, and the only way you can send data from one device to another device is the packet has to be encapsulated in a frame. It's like you, as the packet, if you want to go to the airport, you cannot walk on the highway to get to the airport. You have to be encapsulated in a car, right? The car is the frame. So that frame travels to the airport, and when you get out, the airport is like the router. The packet gets out of that car, the frame, and gets into another frame, whatever, maybe it's a PPP frame or a fiber optic frame or a wireless frame. Okay, so I have to have my MAC address where you're coming from on the car, and the destination address of which is the airport, the MAC address of the airport. So when you're sending frames, you're identifying on the frame where that packet coming from. Where that frame is coming from, or where is it going to? It's inside the LAN. We use our physical names to communicate with each other when we are inside the LAN. When you want to communicate with somebody outside, then you use your IP address, your zip code, in other words. You only communicate, you say, I'm from this LAN, I'm from that LAN, and so on. The port number identifies inside the LAN what application is being used. Okay, because otherwise when it gets to the PC needs to know, what application should I use to open up that piece of data that just walked in. And that's how your computer can differentiate between the incoming data. If it's an email, or if it's a downloaded file, or if it's streaming video that you are sending, right? Port numbers identify that. All right, here are the societies that regulates a lot of the standards, the communication standards in telecommunications. From the Internet Society, I guess the IETF is one of the biggest ones when it comes to the Internet. A lot of the things go through them. The IEEE are the ones that hold or house all the LAN protocols, such as the 802.3 for Ethernet, 802.5 for token ring, and so on. The ISO, the International Organization for Standardizations, they are part of the ITU, the International Telecommunication Union, and they are the ones that came up with the 7 layers of the model. They said we want the data to be encapsulated through 7 layers instead of 4, like the TCP/IP model. We'll discuss that in a few minutes. All right. So those are some of the societies. They're good to know. You should be familiar with who they are. Um, Otherwise, technically, you should know where to go to just in case you need to know something about, for example, anything about the internet. You go to the Internet Society Association. I'm pretty sure you can be a member of all of these and get all the latest and the greatest information about, what's coming up next. What are we looking at in terms of the Internet 2, and how the standards are going to change and things like that. That's something that you should keep up with, definitely. The IEEE is one of the biggest society, nonprofit society in the world, and like I told you, they hold the they house all the metropolitan area network and local area network standards under the 802.3 series. So as you can see, Ethernet working group is 802.3, 802.11 is the wireless LAN, .15 is the Bluetooth, .16 is the WiMAX, and so on. And there are many of them that are growing, in fact, and it's still growing. And you can submit any, if you think that you have something to say about LAN standard, just send it in to the IEEE. They'll review your papers, and it may be published, and then you can receive royalties from anyone that wants to use your standard. All right, so the International Organization for Standardization, as I have mentioned earlier, said that we should have the data get encapsulated through 7 layers instead of 4, just to get into more detail. And you should remember these layers, because you'll be asked either on the CCNA, regular exams, and even in interviews. The best way to remember it, I have a mnemonic for you if you want to use it. Here we go. All people seem to need data processing. And that's from the top to the bottom. From the application, presentation, session, transport, network, data link, and physical. Okay. Now there are other standard organizations such as the EIA and TIA. They get together and they set standards on cables and pins. Which pin is going to have the voltage, which one is ground, which pins are going to be transmitting on the wire and things like that. We'll talk about that when we talk about transmission media. The ITU is the one where ISO came from. These are organizations that meet every 4 years for the whole world to set standards for the whole world in terms of data communications and voice and so on. The Internet Corporation for Assigned Names and Numbers, they are the big guys that take care of the whole Internet addressing, and that includes the Internet Assigned Number Authority that broke down the whole world into 5 regions and assigned IP addresses accordingly. All right, so going back to the TCP/IP model and the OSI. TCP/IP model, like we have mentioned earlier, has been done from the early 1970s, and by the 1980s, the ITU created another organization called the ISO, the International Organization for Standardization, and they went out and said, we want a standard for the whole world, not just for the United States, for the whole world to communicate with each other. So they used the United States DoD model, the Department of Defense model, TCP/IP model. They took the TCP/IP model and broke it into 7 layers instead of 4. They took the top 3 layers of the OSI, made it into an application layer. The transport was left the same. The network was left the same, but they changed the name from internet to network. And the network access was broken into 2 layers, data link and physical. Okay? And these are the protocols. But everyone still uses pretty much the application layer. The TCP/IP model is still in use. But when you're trying to describe how data gets encapsulated, the OSI model is probably the best way to go through explaining how data gets encapsulated. And you have a better clarity of how that works. Again, you should remember the 7-layered model. So, question number 3. What are the 7 layers of the OSI model and how they relate to the TCP/IP model? Right? And there they are. Here's your answer. So that would be your answer right here. The relationship between the OSI model and the TCP/IP model. All right, let's talk about how data gets encapsulated step by step. So that's important. All right, the first thing that you need to know is when you want to send out data and you are going to share the segment with someone else, you got to take turns, right? So you can't just go in there and send data by yourself. You got to make sure that that's called multiplexing. Everyone takes a turn on TDMA actually, time division multiplexing. So everyone will be assigned a certain interval of time trying to use this trunk to get to the server. And your data has to be labeled, sequenced. For example, if you're sending pieces of data, you're going to say this is number 1, this is number 2, this is number 3 packet. So when this guy gets it at the other end, is able to reassemble the data back together. Okay, so let's say we're sending out an email, and at the application layer, that message is called data. You know, the email software on your computer will take the message that you sent, convert it into ones and zeros, and we'll call that data. And when I'm talking about the application layer, that includes the presentation and the session. And that data is passed to TCP. And TCP, what does he do? He breaks up the data into smaller segments. So data at the transport layer is called segments. What do we place at the segments? Sequence numbers to make sure that the receiver is able to reassemble the data, and port numbers to make sure that the receiver knows which application is being used, what's inside those segments, what application he should use to open up the segments. And then these segments from TCP is passed to the network layer of the OSI model. Now the network layer, there's IP in there. IP grabs these segments and places them into packets. What do you place on the packets? IP addresses. And the IP addresses identify the source location, LAN, and the destination location. You know, location, what I mean is like a zip code. That's what these IP addresses for, just the location. Okay? And these packets then is given to your NIC, your Ethernet or wireless NIC, and these packets are then placed in frames, and on the frames you place your MAC addresses, and because your MAC addresses is going to identify who is the sender of the frame and who's going to receive the frame. Now, who's going to receive the frame is not necessarily the guy all the way at the other end. It might be your router, and your router pulls the packet out and reframe it and sends it out. Now, once the frame is placed on the wire, it is placed in bits. So, what is the protocol data unit? Or the PDUs are another word for, you know, what is the name of the data as it gets encapsulated from top to bottom, or de-encapsulated from the bottom to top. So at the application layer, it's called data. At the transport layer, it's called segment. At the internet layer, at the network layer, it's called packet. At the data link layer, it's called frame. And at the physical layer, it's called bits. It's question number 4. What are the PDUs at each layer of the OSI model? In other words, what is data called at each layer of the OSI model? And there you go, we just went over it. All right, so here is your data from the application layer. From here to here is when you put some stuff on it, labels. That makes it a segment. This whole thing will be a segment. And then the segment is encapsulated in a packet. So from here to here is your packet, because you put some additional labels on it. And this whole thing is a frame. And that's why transfers on the wire in bits. De-encapsulation is pretty much grabbing a frame, opening it up, pulling the packet out, then open up the packet, pull the segment out, open up the segment, and pull the actual data out, going the other way around. Okay? All right, so now if you want to communicate with somebody in your LAN, okay, so here's an example. Let's say you want to reach your file server right here inside your LAN. So what you do, you go on your computer, you go File, and let's say you want to print, or you double click on an application that says File Server, whatever, FTP File Server. So your computer goes into the DNS server, gets the IP address of the FTP server, gives it to you, so you put it on your packet. You get your IP address, so it's the DNS server that helps you get the destination IP address. And then your computer has his own IP address, the source IP address, and he gets that usually from the DHCP server. So you place those two on the packet. The packet gets encapsulated in a frame, then you put your MAC address on it, right? Now you need the MAC address of the FTP server. So what do? You send out what's called an ARP request, an Address Resolution Protocol address. Because you know the IP address of the FTP server, you say, hey, whoever has this IP address, you tell everybody on the LAN, please give me your MAC. The FTP server recognizes his IP address and gives you your MAC, his MAC. You take the MAC, you place it on the frame, and when you send the frame to the switch looks at the destination MAC address stamped on that frame, knows where the server is located, and sends them that frame. And that's it. Now, if you want it, that's what it really comes down to, okay, using the ARP request. And by the way, he'll remember that MAC address, so he doesn't keep doing this ARP request thing. Now, when you want to communicate with somebody in the outside world, what you're going to do is, let's say you went to yahoo.com. You type in www.yahoo.com. Your computer goes out to the DNS server outside your LAN, gets yahoo.com server IP address and gives it to you. You stamp that on your packet. You put your IP address in there, and then you put that packet in a frame. You're ready to send it out. Now your computer thinks yahoo.com server is located inside the LAN. So he does an ARP request. Hey, whoever has this IP address, please give me your MAC. Well, yahoo.com server is not here, so nobody's going to respond. So what's going to happen? Then your computer by default goes to the gateway, which is your router. Say, hey, gateway, my post office, give me your MAC address. I need to send the package outside my LAN, because most likely yahoo.com is outside because nobody responded here. So your router gives you the gateway gives you his MAC address. You encapsulate that packet inside a frame and put the destination MAC address as the gateway. And then you send that frame to him, the router that is. The router pulls the packet out, looks at the destination IP address, and figures out which other router he's going to send the data to, and then we encapsulate it into another frame and sends it out. Okay, that's why we all need to know the IP address of our default gateway, so that if we are not communicating with anyone inside our LAN, by default we go to the gateway. If you don't know your IP address of the gateway, you can never ask for his MAC address, and therefore, if you can never get his MAC address, you can never send him any frames. And if you don't send him frames, your data will never leave your LAN. That means you can never access the outside world, outside your LAN, but you can still communicate with anyone inside your LAN. All right? So you need a MAC address to communicate with people inside your LAN. You need an IP address because that's how you are identified outside. The IP address identifies the location of where you are. Okay? The MAC address identifies who you are inside the LAN. And that's why you use frames. All right, so that's your default gateway. We discussed that already. And we discussed how you can communicate with the outside world as well. All right? So, hopefully this was a pretty informative chapter for you. So, again, please answer the questions that I gave you and submit them in a separate Microsoft Word. If you have any questions, you can always email me, of course. And I'll talk to you in chapter 4. Good luck.